Let's do a simple rotational kinematics problem. Here are the main kinematics equations in rotational form. Remember, you can simply exchange the translational variables x, v, and a with the rotational variables theta, omega, and alpha, because both equations are derived the same way. So here's an example problem. After loading your washing machine, you push the start button. The drum inside the washing machine starts spinning from rest and rotates through 20 revolutions with a constant angular acceleration before reaching a constant angular speed of 5 radians per second. What's the angular acceleration during this first 20 revolutions? How long did it take to complete the first 20 revolutions? Pause the video now and try this for yourself. Then turn the video back on and I'll work through the solution. So the first thing I always do is make a chart like this. Theta initial, theta final, omega initial, omega final, alpha, and t. I've filled in what I know. I know theta initial is 0, and it goes through 20 revolutions, so that's my theta final is 20. Omega initial 0, omega final 5 radians per second. We are trying to find alpha and t. The first thing we have to do is make our units all match up, because these kinematics equations work for any units you want to use as long as you're consistent. If you use theta in degrees, then you need to use omega in degrees per some time interval, maybe seconds, and alpha has to be in degrees per second squared. If you chose revolutions, theta could be in revolutions, omega could be in revolutions per second or per minute. I'll use seconds. And then alpha would have to be revolutions per second squared. You have to be consistent. If you choose radians, theta could be in radians, omega could be in radians per second, alpha could be in radians per second squared. As long as you're consistent, you can use whichever units you want. But you have to be consistent. And this is true of kinematics equations. What should we use? Why don't we use radians per second for omega, and that means we'll get our answer for alpha in radians per second squared, but we need to convert theta from revolutions to radians. So we need to multiply by 2 pi radians per revolution, and we get 40 pi radians for theta final. Which one of these do we want to solve for first? Let's pick an equation that's missing t, and we'll use that equation to solve for alpha. So we're going to have 5 radians per second squared, and 0 is our initial. Alpha is what we're trying to find, and this is 40 pi minus 0. And I get alpha 0.1 radians per second squared. Now we can find the time it took. We can use this answer and any of our kinematics equations. The first one is probably the easiest, but if you don't trust that answer, then use one that's missing alpha and use that equation to find t. That would be the last equation. I'll do that. So we know our theta final and theta initial, and we add to that t multiplied by the average angular speed. Theta final was 40 pi, theta initial was 0, omega initial was 0, omega final was 5, 80 pi over 5. .3 seconds. That problem was fairly straightforward. Let's look at one that's a little more interesting. You push the start button on your washing machine. The drum inside starts from rest and has a constant angular acceleration of 0.15 radians per second squared. After 20 seconds, you notice you forgot to add detergent, so you open the lid. Opening the lid activates the safety switch, cuts power to the drum, and it rotates through 4 revolutions with a constant angular acceleration before coming to rest. And a couple of questions we can ask about that. Through how many revolutions did the drum rotate from the initial pushing start until the final time when it comes to rest? Through the entire period. and how much total time elapsed from the time you push start until the drum comes to rest at the end. Pause the video, give these a try, and then resume the video to see my solution. So the problem with kinematics equations is that they're only good when the acceleration is constant. In this problem, during the first part of the problem, alpha is constant while the drum is speeding up. I'll call that alpha 1. In the second part of the problem, alpha is constant while the drum is slowing down. I'll call that alpha 2. The problem is that alpha 1 and alpha 2 are not the same. So in order to do this problem, we'll split it up into two problems. One is the time interval when the drum is speeding up. During that time interval, we have a constant angular acceleration, alpha 1. We can use kinematics equations. Then in the second time interval, alpha 2 is constant, and we can use kinematics equations there. But we can't cross over. We can't start at the beginning and end at the end with the kinematics equation because alpha is not constant over that entire time interval. We can only use kinematics equations over a time interval where alpha is constant. So the first thing I'm going to do is fill in my missing quantities during my first time interval while the drum is speeding up. I know three things. I know the time, I know alpha, I know omega initial. I can solve for omega final and the final angle. I'll find omega final first. And my units are radians per second squared and seconds, so I'm just going to stick with that, and I'll find omega in radians per second and theta in radians. So I know omega final now, and I can solve for theta final. I'll use this equation. Omega initial is 0. Omega final is 30 radians. This is during the time interval where the drum is speeding up, my first time interval. So I've got all the information I need. Now I want to look at that time interval where the drum is slowing down. What do I know there? I'm missing a lot of information. I know it ends at rest. I know omega 2 final is 0. It ends at rest. And I know it went through 4 revolutions. So my theta final is my initial plus 4 revolutions. And that's all I know. Let's see what other information is here that might help us out. Well, we know that this whole time interval 2, when the machine is slowing down, when the drum is slowing down, occurs right at the end of time interval 1. So if I end at 30 radians, then that means I'm starting my next time interval at 30 radians. I end at 30 radians plus 4 revolutions, so I'm going to convert 4 revolutions into radians. I'll probably just continue using radians. And I know that I ended my first time interval with an angular speed of 3 radians per second, so that means I'm starting my next time interval at 3 radians per second, and I'm ending at 0. So now I know 3 things. I know delta theta is 4 revolutions. Let me write that in here. Delta theta, 4 revolutions, 8 pi radians. Now I can solve for alpha 2 and t, so let's do that. So this equation is missing time, so I can use it to solve for alpha 2, and I get alpha is equal to negative 0.18 radians per second. And it's important to realize that this answer had to be negative because alpha and omega are exactly the same as a and v. Remember back to our linear motion, when the acceleration and the velocity had the same sign, when they were in the same direction, the speed was increasing. So in this case, omega and alpha were both positive during our first time interval, and the speed was increasing. The drum was going faster and faster and faster as time went on. And in the second time interval, omega, if it was positive in the first time interval, has to be positive in the second time interval because the drum is still spinning in the same direction. clockwise or counterclockwise as you look down into the washing machine from the top. If the omega's the same, then alpha has to be the opposite sign because now it's slowing down. Alpha has to be negative, omega positive, and we end up with a slowing motion, just like linear motion. So that answer makes sense to me. I'll just write it in here, negative 0.18 radians per second squared. And let's find the time interval. Final is omega initial plus alpha t. 0, 3 radians per second, negative 0.18. 16.7 seconds. So now you can answer the questions. We've filled in all the information in both charts. The total time is 20 seconds for time interval 1, 16.7 for time interval 2, so you add those up to get the total time of 36.7 seconds. And the total number of revolutions is 30 radians plus 8 pi radians. That gives you the total angle traveled. If you wanted it in revolutions, you could convert that to revolutions. And you have all the information here to answer the questions. So remember, kinematics equations can only be used when the acceleration is constant. If they give you a complicated scenario like this, where there are two regions of time where the acceleration is not constant from the beginning to the end, see if you can break it up into multiple time intervals where the acceleration is constant over each one of those time intervals. And then you can use kinematics equations within the time interval, and then you link the time intervals together. The end of time interval 1 is the beginning of time interval 2, and see if you can get enough information that way to work your way through the problem. Remember, these problems are like puzzles, and sometimes it looks like a piece of the puzzle is missing. But then you realize that maybe I can solve for the missing piece so I can finish the puzzle. And that's what makes them so much fun.